Right. See, if you recall, I told you that tautomerism occurs, because of the migration of hydrogen from one place to the other place. One of the main components of the tautomerism is keto-enol tautomerism, and it gets enhanced in the presence of basic medium or in the presence of acidic medium, which means enol will start converting into ketone and ketone will start converting into enol, vice versa, in both the cases. Usually, you will find out the rate of tautomerism is much better in basic medium as compared to that of acidic medium. These are the few pointers that we learn. Now, notice that when it comes to percentage of enolization, it mainly depends upon the factors like how much there is an extended conjugation. Is there any intra-hydrogen bonding or not? What is the nature of solvent? If at all we have, sufficient acidic hydrogen or not? And what are the inductive and steric factors? Aromaticity, correct? Temperature and what is the phase of the compounds. These are few important pointers that we need to check. Now, notice something. Generally, when it comes to conversion of ketone to enol, right? Basically, what you're doing is you're trying to break a bond between carbon oxygen. I mean, you're breaking a double bond and making it to a single bond. You can see that you're making it to a single bond. So that means there is a disturbance in the bond here and here. So imagine as if you're breaking this completely. You're breaking carbon hydrogen bond completely. And then you're also breaking this carbon carbon bond. So these are the three bonds you are breaking. Imagine like that. Similarly, here, to bring back towards ketone, you will be breaking oxygen and hydrogen bond, carbon and oxygen bond, and carbon double bond. So imagine you are breaking all those bonds here also. If I add the bond energies on the left hand side and on the right hand side, you would notice that on the ketone side, you will require more energy as compared to that of enol side, which present you the fact that the ketones are generally thermodynamically more stable. That means, as comes to thermodynamics, stability is the concern we need to check out, and ketones relatively are more stable, which means reactants require more energy to be broken into products. So, usually, what you notice at a normal room temperature, if you observe the equilibrium constant, it would be more towards the ketone rather than towards enol. You know that delta G will be 0. If you recall the formula from thermodynamics, you know that delta G can always be represented as delta G naught plus RT ln K equilibrium. Sorry, KQ, ln Q. And if delta G is equal to 0, then that Q will become K equilibrium. Hence, delta G naught will be equal to minus RT ln K equilibrium. And that's what I have written here. At equilibrium, delta G is 0 and delta G naught is minus RT ln K. Imagine these two cases. Imagine I have 1% of enol, 99% of ketone, and 99% of enol and 1% of ketone. So when you have 99% ketone and 1% enol, K equilibrium will be 1 divided by 99. And when ketone is 1% and enol is 99%, then it is 99 by 1. If I substitute that value, I'm getting delta G naught value is 11 kilocalories, and here as minus 11 kilocalories, which means if you want to convert a 99% of the ketone into 99% of the enol, which means you will have to add 11 minus of minus 12, minus 11, total of 22 kilocalories of energy to be added, isn't it? So imagine if I want to convert a ketone completely, almost 100% of ketone into 100% of enol, I have to spend approximately 22 kilocalories more amount of energy. You notice this, suppose if I get an enol compound and in an enol there is a hydrogen bonding developed. A hydrogen bonding will release an energy approximately 30 kilocalories, which means it is a sufficient amount of energy which is required for ketones to convert into enol. Similarly, an aromatic ring formation in the enol can release an energy of 35 kilocalories. What is the learning from here, everybody? That is, ketoenol tautomerism is extremely sensible in terms of some stabilizing energies. That means if you get any stabilizing energy towards enol, the reaction will, quickly shift from ketone to enol. Got it? That will shift from ketone to enol easily. Okay, and that's what you will observe here. See, arrange the following according to the decreasing order of the enolization. If this is what has been asked, so you can see triphenyl carbon with CHO, phenyl CH2 and CHO, diphenyl carbon and CHO. Suppose if this is how it is given. You know that in the first case there is no participation of enol only. I mean there is no alpha hydrogen, so there is no tautomerism. Here there is some tautomerism. Here there is more tautomerism. You can see here it would have more amount of resonance because this enol will offer resonance from this phenyl group as well as from this phenyl group. While in this enol, you have only one phenyl, which means this will give you better enolization compared to that of 2, compared to that of 1. So 2 is greater than 3 is greater than 1. This is the order you need to learn. Likewise, when it comes to A, B, C, D, E here also, you would notice that if I remove the hydrogen from here, you can get the negative charge can push here, the pi bond can push here. Or this negative charge can push here and pi bond can push here. That's how, again, the rate of enolization can increase. Notice one thing, while this negative charge is pushing, if already there is a lone pair which is giving resonance, so this pushing of electrons becomes weaker. Hence, if there is an ester group or a diester group, their enolizing factor is very weak. Even when there is a methyl group, due to hyperconjugation, this will also have a donating effect, and that will hamper the resonance on the other side. Therefore, this one is also starting to show some weaker resonance factor. So the best resonance factor is observed is A, then B, then C, then D, then E. Is this point clear to everybody? Okay. This point is clear to everyone, then you can let me know. You can go ahead. Clear? Yep. Check out. So for this tautomerism, extended conjugation, intra-H bonding are the factors. For this one, methyl hyperconjugation plus side destabilizes, but still possess to have some extended conjugation. Methoxy groups will give you much more plus M effect, so that will destabilize extended conjugation. Second factor, if there is any donating group, that will decrease the resonance effect, correct? But if there is any withdrawing group, that will increase the resonance factor. So you can see B is greater than C is greater than A. So more the withdrawing group, more is the rate of A. Now notice A, B, C, D. A, B, C, D is very similar to the earlier first, the second case here. So here you can see there are only diketones. Here we have keto and ester, diesters, diamides. Diamides are the worst in tautomerism. So therefore A, B, C, D. 1, 2, 3, 4. You can see this is completely aldehyde. So that is best. This is also aldehyde. Aldehyde with an extended conjugation, because here we have again a benzene group. So that minus charge can get resonance stabilized. So this will have much more extended conjugation. So 4, then 3, then after we have 1, then 2. 2, there is a donating factor which will destabilize. So 4, 3, 1, 2. Correct? Notice here we can have A, B, C, D, which is a very similar case. This is diketone, this is ketoester, this is diester, this is diamine. So A, B, C, D. Now, in the case of acidic medium, you will notice the enol stability is what you need to compare more strongly. Okay. So if you compare the enol stability, you have to check out the stable double bond character. Here this double bond does not have any effect. Here there is one methyl, here there are two methyls. Two methyls will show more hyperconjugation. If I put in terms of alpha hydrogens are 3 here, alpha hydrogens are 6 here. So this will offer more amount of hyperconjugation as compared to this one, as compared to this, which is 0. So CBA. And this I told you already, I remember all of this part, that why, in which case, what is the reason. In the first case, thermodynamic factor is the reason why ketone is more stable. Second case, same logic. Third case, anti-aromaticity, that's why it is 0% in enol. Fourth case, it is aromatic, that's why it is 100% in enol. Hydrogen bonding, so again 100%. Acha, aromatic ring also and hydrogen bonding also. Next, here also aromatic and hydrogen bonding, so 100%. Got it? Here you can see 10 raised to power of minus 3. So in both cases, you will notice that you will have a diester oxygen which can form resonance, stabilizing on their own. Lastly, here there is a hydrogen bonding with some resonance factor. So beta keto is slightly okay, but still the percentage is very less. Okay. So these are few factors which I wanted you to check in all of these cases. Okay. Now this is something which I ask you to try as well. Let's quickly do this. First case, A versus B. See, in the case of A, this is the enol what you will get. In the case of B, you will get an enol like this. Have you noticed in the case of A, we have an extended conjugation. That's why A will show better enolization than B. Second, same logic in the case of chlorine, you have an extended conjugation here. So again, A is better than B. One second. Right. Notice in the case of A and B, you can see if I make a double bond here, you can have an extended conjugation. Here you will have less extended conjugation. In fact, there is no extended conjugation on the other side. Therefore, A is better than B. Now, if I take these three cases and write the enol form, these are the enol forms. You can see here there is a double bond. Here a double bond is there. Problem what happens with the double bond here is this double bond has to be over already existing strained ring. There is not much of a problem. So therefore, better version is always A, then C, then B. Got it? Clear with that? Next one. Next, A, B, C. C for A, this is the enol form. For B, this is the enol form. For C, this is the enol form. In the case of C, the resonance factor is so much that it is aromatic. So C is better than B, than A. The fifth case is clear. See the sixth one. Here this has enol. Here for this enol, it has becoming anti-aromatic. But for this enol, the ring is becoming aromatic with hydrogen bond. So C is far, far better than A, and A is far, far better than B, because B will never exist in the enol form. It will only exist in the keto form. Okay. Same logic here. A, B, C. C becomes aromatic. B has extended conjugation. A does not have anything. So C greater than B greater than A. Next, here you can see this one will have, this one will have aromatic nature with enol, correct? This one cannot show aromatic nature because once we get a double bond here with OH, okay, it becomes difficult to get an aromatic form. So A is greater than B. Between these two, it is an important exception. Remember how I'll show you with the structure also. I can have O and H here with a double bond and double bond O making a hydrogen bonding here. Problem with the B is it will try to exhibit always in that anti form. Here the rotation is not possible even though it is single bond. Reason being, in the anti form only it will have least repulsions. If you try to bring it to this side like this, then the lone pair repulsions will be very high. That's why to avoid these lone pair repulsions, it will always exist in the keto form. So therefore, A is far greater than B. A is going to be highly in enol form. B is going to be highly in the keto form. Okay. Next point again in ABC, if you write the enol forms, check out here. If at all I have to write the enol form, this is the enol form which I'll get, which is anti-aromatic ring. Here, if at all I get OH with double bond. Next one, what I'll get here is OH this way. Okay. So now if you compare, here there is some amount of strain developed. This is a highly unstable form because of anti-aromatic. So which one is better? B is better than C is better than A. Okay. Next one. Here, if you notice carb anion coming across this point, likewise we have double bond O minus double bond O here. Then double bond O with minus double bond O with minus. You can see here there is an extended conjugation in all three directions. Okay, here also, and here also. Here extended conjugation in two directions. Here there is no extended conjugation. Hence, A is greater than B is greater than C. Okay. So I hope all of you got an idea how to check out the tautomerism part here. Now, the second important application of tautomerism is that it shows kinetic isotopic effect. Due to tautomerism, it will exhibit something called kinetic isotopic effect. Now, what is it exactly? Check out. It is the isotopic effect of solvent. That means if you have a keto group, as you react with OD minus or D2O, if you react that with OD minus in the presence of D2O, second, yeah, sorry, check. You would notice all the alpha hydrogens are getting replaced by deuterium. Of course, this will take some long time, but replacement is evident. See how the mechanism works. OD minus as a base will extract H plus. We'll get this enolate ion. Enolate ion will show tautomer resonance effect like this. And when we get CH2 minus, the CH2 minus will take deuterium from water, heavy water, remove out this OD minus. So again, you can see the H got lost and D got introduced. Why is this happening? Because the carbon deuterium bond is relatively stronger than carbon hydrogen bond. That's the only reason. Okay, deuterium bond is stronger than hydrogen bond. So this will keep on happening multiple number of times. So OD minus will take H plus from here, gets minus charge here. Again, it will get two deuteriums. One more time, it can remove this H plus, it will get three deuteriums. And the same logic applies to on the left hand side also. So as long as all the deuteriums are replaced, it will keep on happening. Okay. So now this is one standard JE question which will be asked, like how many number of deuteriums are exchanged in a particular molecule. For example, if the question is given acetaldehyde, answer is 3 because alpha hydrogens are 3 of them. Next, if you have this butanol, you can see 3 here and 2 here, total 5. 5 deuterium exchanges are observed. In the case of phenol, OD minus will take H plus, you get O minus. That can be shown as a resonance stabilization in the keto form like this. Now, in this keto form, if you notice that this is the alpha hydrogen, okay? Here is the alpha hydrogen, sorry, here. And in this case, here is the alpha hydrogen. In this case, here is the alpha hydrogen. So that means here, here, and here, hydrogen exchange can be happening. So all of them will convert into deuterium forms. And when you get it back into the phenolic form here, these deuteriums will remain and this H has been also replaced by deuterium. Total how many exchanges will happen? 4 exchanges will happen in this case. Got it? So this will have 4 exchanges. Now I want all of you to try doing the number of exchanges in these two cases. Please check everybody. Please try doing it along with me. How many number of deuterium exchanges will happen in this case? Let's start in the first case. Check out. Double bond O here. You know that minus can come here. That means deuterium exchanges are possible on this case. So in the presence of OD minus and D2O here, so you will definitely see these hydrogens are replaced by deuterium. This is one form. See, another form is when you take this and react with OD minus and H2O, you can get minus here also. So that means this is CD3, minus can exist here as well. See, now this minus can undergo resonance stabilization as well. So which means double bond can be pushed here like this and this pi bond can be pushed here. So minus charge can come at this point also. CD3. Okay. Which means wherever there is a minus charge, if you react with OD minus and D2O, here also OD minus and D2O, they will start replacing the hydrogens on that position. So here we have two deuteriums, two hydrogens, both will get replaced by deuterium. CD3, correct? And here also, if you notice that we will have double bond, we can get this as CD3 and CD3 here, correct? Here already there is a deuterium replacement like this, okay? So finally, this is where you will reach at the end point. This is where you will reach after all the prolonged time. One deuterium exchange is here. Sorry, original compound we have to write first. Sorry, my mistake. The original compound is like this: double bond here and double bond O here. Now see what are things I'm writing. C D3 here, two deuterium here, and two deuteriums here. These were all the exchange positions. So what you need to do, everybody, that you need to check out which all position your carb anion is moving. Wherever the carb anion is moving at all those conditions, at all those positions, you can make deuterium exchanges. So, in short, total number of deuterium exchanges here are 7. Okay, please check this first case. I hope that is clear. Right. The second case is pretty similar to that. You can see in the second case, what's happening here is like this. You can have double bond O. Minus charge can come at this position. Similarly, minus charge can come at this position. And due to resonance, like this, minus charge can come at this position. So you compare all these three cases, and then now in the final case, make all the deuterium exchanges, which means now you can see in these cases we have CD3 here, double bond is already here, which means one deuterium exchange here, and CD3 here. So number of exchanges. So number of exchanges. If you compare, so how many exchanges we are getting here? So you can see 3 and 3, 6 plus 1, 7. Total we get this as 7 exchanges, which is same as the earlier case. Please do check, everybody. Done. Right. See the next one. In case if you have a ketonic group like this, so how many exchanges? This side I can't make any exchanges because I do not have any alpha hydrogens which is compatible for tautomerism. Hence, to keep it like this, here double bond O, this side nothing. But here minus charge can come here first, and due to resonance, minus charge can appear here as well, like this. Now if I put all of them together, so what would I get? Here I would get two deuteriums, correct? Originally double bond is here, so which means one deuterium here, and this double bond has no role on it. So therefore number of alpha hydrogens that can be, sorry, number of deuteriums that could be exchanged in this case will be 3. So 3 deuterium exchanges are possible in this case. Clear? See the next case. Next case, if I put the structure the way it is, double bond, double bond O, like this. So you can see minus charge can come here first. I'm putting all the minus charges from where the tautomerism can be shown. One minus charge can be here. One minus charge can be here also. Next, another minus charge which it can show here would be on this position. Here also, it can show minus charge here, which can push the resonance to happen. Another one, the minus charge could be on this side also. This is the cases where you can see tautomerism can happen. Now, resonance. From here, can you see resonance can also take place? That means this can push here. This minus charge can come here. So, which means, in short, we can have double bond moving here and negative charge coming at this position. This is one way we can have. Okay. Likewise, on the right hand side also we can do the same thing. Minus charge is here. So now I can use resonance, push here, the pi bond can be pushed here, and from there we can get movement of the electron. So we will get this as double bond here and minus here, correct? So many resonating structures we can get. Now Let me put at the end all the deuterium exchanges that possible. See, two deuteriums here, two deuteriums here, three here, three here, one here, and one here. That's it. These are all the alpha, I mean, number of deuterium exchanges that are possible. So how many we get? 3, 3, 6, 6 plus 4, 10, 10 plus 2, 12. So total 12 deuterium exchanges are possible. Please go through it. I'll give you a minute's time. Okay, then we can go ahead. Please go through all the cases. See the next one. In this case, there is no alpha hydrogen which can make a tautomerism happen, right? This said there is a double bond, double bond. We learned this that tautomerism cannot happen unless there is an sp3 carbon in conjugation. Same logic here also. But this said we have these two. So that means only two of them are possible in this case. For this one, only negative charge where you can get is minus here with a double bond. That's it. This is the only case which is possible. Correct? Rest all case it is not possible at all. Done. So this is a very important concept about number of deuterium exchanges possibility. Lot of questions are there in assignment copy which I have uploaded. So when you start, tautomerism is separate topic altogether. Some institutes teach it completely different. Some institute teach it as a part of structural isomer. Correct? Nevertheless, you have to start solving a separate assignment for uh, tautomerism. Okay, which I have uploaded. So please do check. Next, what are the different types of tautomerism other than ketoenol? The first one being nitroacinitro. See, this is the nitro structure, alkyl nitro group. In the nitro group, if you make this hydrogen to migrate here, correct? And then here, sorry, more than here, here. If at all I migrate here, this double bond will shift here. And this is what you will get. And this is called acinitro. So nitroacinitro tautomerism is always observed. Next, nitroso-oxime tautomerism. You can see this N double bond is nitroso. And if I push this double bond here and make this hydrogen to go here, this is called oxime. Stability wise, nitroso is more stable than oxime. Next, cyanide enimine tautomerism. This is cyanide. And if I push this hydrogen here, double bond here, that will become ene plus imine. So enimine. So cyanides are generally more stable than enamine. That's why you will see this tautomerism is weaker. Majority of the content will lie on the cyanide side. A very small composition will go into enamine form. Amido imido tautomerism. This is amide, right? Amido. And if you make this double bond shift here, oxygen shifts here, that will become imido. And amidos are very, very stable compared to that of imidos. So again, tautomerism mainly lie on the left hand side. Next, lactam tautomerism. See, lactam is a cyclic amide, and that in the presence of base can make this hydrogen to push here, double bond to push here. That is called lactam. So hence the name lactam tautomerism. Next, enamine tautomerism. So C double bond N is imine. If I push this hydrogen here, double bond here, that will become enamine. Imine will become enamine. Next one is para-tautomerism, which is 1,5 tautomerism. At one position, I have hydrogen. From one position, if at all I push this to the fifth position and keep pushing the double bonds here, so that will become phenol. So this is called para-tautomerism or 1,5 tautomerism. Next is quinoxide nitrosotautomerism. See, this is nitroso group. And then if I make this hydrogen to move all the way here, double bond to move here, and all the double bond moving from here to here. So that will become quinone. Okay, quinoxime, sorry. Quinoxime. Let me write correctly. This is called quinoxime. Yeah. So it is nitrosoquinoxime tautomerism. Okay. Next few special cases includes internal tautomerism, like you have here. So this double bond can be made between carbon nitrogen and hydrogen can be shifted here like this. This is called 5-azacyclooctane. Okay. And this is like nitrogen bridged compound. So this can also be a part of a tautomerism. Here you can see this is like an aldehyde and an alcohol part. So again, this double bond can be shifted here. Oxygen can be attached here. So what happens? See, this hydrogen has completely shifted here, and this double bond being made a bond with oxygen. So this is also a type of tautomerism. Next, three carbon system tautomerism. There is a double bond and double bond here. This is alpha hydrogen. This is alpha hydrogen. If I remove this, making a negative charge, and that is pushed here, I mean that negative charge. Well, you get a negative charge here. So that means you are trying to push a double bond here like this. Or you can do the same thing on this side also. Here it is explained on this basis. See, I'll explain on this side. I got a minus charge here. I have a double bond here. So what I'm doing is this double bond I'm pushing it here, minus charge I'm pushing it here. So what would happen now? I have a double bond here. Now I have a double bond here and a minus charge here. And that minus can take the H plus which is lost. Therefore, this part is converting into this part now. Okay, that is after putting the hydrogen here. Likewise, is the same thing. If this can be getting a minus charge on this end, double bond can move here, and this is another tautomerism. Same way, an isolated double bonds can be converted into a conjugate double bond in the presence of basic medium. These are all a special type of tautomerism. Okay. See, next, what is the effect of the solvent in this tautomerism? See, in the presence of non-polar solvent like CCl4, the percentage enol increases. The percentage enol will always increase in this case. Okay. Because more the non-polar solvent, right? More the non-polar solvent. In that case, if the person, what would happen here is the hydrogen bonding which will happen in the enol form or any conjugation that happens in the enol form, that will only stabilize the factors. But in the presence of polar solvent, the hydrogen bonding or any conjugation, that is not going to help, because even the ketone will be stable in the presence of polar solvents. Let me show you with an example. Suppose if you have a keto group here, this ketone can have a lone pair and lone pair here connected with water molecules. This is anyway getting stabilized. Ketone is also getting stabilized. And enol, if you have, enol will also getting stabilized. So there is nothing special about only having a enol form here. So therefore, in polar solvents, both ketone as well as enol both will get stabilized. Okay. Hence is the case. So you see, effect of solvent. What you will notice is that in the presence of polar solvent, intermolecular hydrogen bonding is observed in both of them. So intramolecular is hardly going to make any effect of it. Hence, gas phase percentage enol is the best. N-hexane is also almost the great amount. In its pure form, it is around 76%. I'm talking about this as a reference. And in water, the percentage drastically decreases to 15%. Okay, even though it is in an enol form, there is hardly much difference in terms of intra and inter hydrogen bonding. So remember, as polarity increases, enol content decreases. I'll write down that part here. Okay. As polarity of solvent increases, okay, percentage enol content decreases. Okay. Next, what is the effect of temperature? See, as long as the temperature is increased, thermodynamically, because ketone is more stable, the ketone content will increase and the enol content will decrease. So remember, as temperature increases, percentage enol content decreases. Okay, and percentage keto content will increase. Okay, right. So these are all the factors which are affecting the percentage enol content. Clear, everybody? That's it. These are all the important pointers that you need to know it from the tautomerism. See, let me give you the crux of tautomerism. First thing, tautomerism is all about migration of alpha hydrogen. Okay. So if I have to just summarize tautomerism, first thing it is migration of alpha hydrogen of sp3 hybridized carbon. Okay. So you can see more alpha hydrogen, more stability. It will have more stability. Next one, we learned that we can have tautomerism happening in solvents, and you will see basic medium is greater than acidic medium. I explained you through mechanism. Next, we have percentage enol comparisons. So in various cases, we are trying to compare what is a percentage enol. Next one is deuterium exchange. Deuterium exchange. And the last one being factors affecting enol content. Factors affecting percentage enol content. That's it. This is the crux of tautomics. Is it all clear? Whatever the cases I have taken, these are more than enough for your exam. Got it? Whatever exams you're going to attempt, this will be more than enough for it. Okay. So everybody, this is the first part of isomerism, which is structural type.